Hey, welcome back. So we have an example here of magnetic boundary conditions, and we've also been talking about magnetization. So this example is going to pull magnetization in with the magnetic boundary conditions. All right, so given that H, the magnetic field intensity, is this thing here, so it's got an X, Y, and Z component in a region that's defined by this thing, where the permeability of region 1 is 5 times mu 0. Calculate the magnetization in region 1 and the flux density in region 1. And then part B, calculate the field intensity in region 2 and the flux density in region 2, where the permeability, or at least the relative permeability, is 2, or the permeability is 2 times mu 0. Okay, so let's get started. So for part A, we know that the relative permeability is 5, right? And we're looking for the magnetization, so we need the magnetic susceptibility first. Okay, and we know that that is related to the relative permeability by this guy here. Okay, or I think in the lecture videos it was 1 plus the susceptibility is equal to mu r, like that. Okay, so either way. But anyway, I'm just going to erase that. So we've got a relative permeability in region 1 of 5. So this is just 5 minus 1, and that's 4. So that's the susceptibility. No big deal there, right? And then if we want the magnetization in region 1, we saw in the previous video that was the susceptibility times the magnetic field intensity in that region. So we've got that guy there, H1. And so if I carry out that multiplication, so that would be 4 times each one of these components. Okay, that's pretty straightforward, I think. So that's minus 8x, minus 8ax, straightforward if I could say it correctly, plus 24ay plus 16az. And that is, magnetization is amps per meter, like that. So that's our answer, or at least part of our answer for part A. Then we're looking for the flux density in that same region, region 1. And so that is the permeability in region 1 times the field in region 1. Alright, so then I just carry this out, this multiplication. So I've got mu 1 is 5 times mu 0, the permeability of free space. So that would be 5 times 4 pi times 10 to the minus 7th, and then times h1, right? So I'll let you do that, punch out those numbers in your calculator, and then up to 3 significant digits, what you find is you get negative 12.6 ax plus 37.7 ay plus 25.1 in the z direction, and I've got that in micro Webers per square meter. Micros 10 to the minus 6. Alright, so that's what we have for part A. So part A was straightforward. Let's do part B. So what we've got here now is we want to calculate the magnetic field and the flux density in the other region. So we have this this equation of this plane, y minus x minus 2 equals 0 is the separating plane, and then below 0 is region 1, and then above 0 is region 2. So we've got the field intensity in region 1, and we want to get the field intensity in region 2. Alright, so first of all, let's talk about that plane. So the separating plane is given by this thing, like I said, y minus x minus 2 equals 0, right? So if you're below that, less than 0, then you're in region 1. And if you're above that, greater than 0, you're in region 2. And we're going to use a trick that we used in a previous example. If you didn't see that video, that's okay. It turns out what you can do is you can write this as a dot product, And so what we can do is we can put x, y, z, 1 dotted with, in this case, -1, because that's the coefficient in front of x, 1, that's the coefficient in front of y, and there's 0z, and then the coefficient in front of the 1, if you like, is -2. And we look at these numbers here, and the idea is that the dot product is 0, right? So if you carry out this dot product, you've got x times -1 plus y times 1 plus z times 0 plus 1 times -2 equals 0. So this is the same equation there. But the idea with the dot product is if two vectors are dotted with each other and you get 0, then they're perpendicular. And so what this means, then we look at these three things, the x, y, z, and this means the normal, then the perpendicular to this plane, which we're going to need, is then -1 in the x direction and 1 in the y direction. And then if I want a unit vector, then I need to divide by its length, which is the square root of -1 squared plus 1 squared, or the square root of 2, right? So our unit vector that is perpendicular to the surface or the interface is this thing here. We're going to need that. Okay, so why do I need that? Well, let's get the normal component of h1. So the normal components, I'm going to project, let's think of our vector operations here. I'm going to project h1 onto that normal unit vector, right? So I'm going to take h1 dotted with an, then times an. So again, when I take the dot product, I get a scalar, and then that scalar times the unit vector gives me the normal component. So I carry out this operation. So I've got h1, so I've got -2 times -1 over root 2, so that makes positive 2 over root 2, like that. And then I've got 6 times 1 over root 2, so plus 6 over root 2. Okay, and then I've got 0 in the z direction. And then times an, so that would be -1 over root 2 ax plus 1 over root 2 ay. This is a y here, by the way. Okay, so again, I carry that out, and I get -4 ax plus 4 ay, and that's in amps per meter, right? And so I'll come back to that, but now that I have h1 normal, let me get the tangential component. So how do I get the tangential component? Well, the normal component plus the tangential component equals the vector. In other words, the tangential component is the vector with the normal component subtracted off, right? And so I've got the normal component, so I'll just do the subtraction, h1 minus h1n, right? And so that gives me, it looks like 2ax plus 2ay plus 4az amps per meter. Okay, so now I have the normal component and the tangential component of the field in material 1. So how does that help me? I'm going to come up here to the top. Well, we know that now what happens across the boundary is that the tangential component is continuous of the field. So this is h2 tangential is equal to h1 tangential. So I'll just recopy that. Just the old copy and paste right there. That is nice, right? So I've got this, very nice. And then the normal component. What happens to the normal component? Well, as we showed, that would be, we have to bring in the permeabilities there, because the normal component is discontinuous, we say. So there is a change that happens there. So we bring in mu1. Mu1 is 5 mu0, right? And then mu2 is given in the problem. That's 2 mu 0. So the ratio is 5 halves. And then, not equals, 5 halves times h1 normal. So we have the h1 normal, and the h1 normal was this minus 4ax plus 4ay, right, amps per meter, like that. And so this turns out to be negative 10ax plus 10ay amps per meter. Okay, so now we're not asked for the normal or the tangential, we're just asked for h. So how do we get that? Well, the normal plus the tangential of any vector gives you the vector. So then we just add those two vectors up, the tangential and the normal. So I'll take the 2 plus the minus 10, that gives me a minus 8 in the x direction. Then I'll take the 10 plus the 2, that gives me a 12 in the y direction. And then I've got a 4 and 0 here, so that gives me 4 in the z direction, amps per meter. Great. Okay, so that's part of my answer. That's the field intensity. And then finally, I need the flux density there in the second material. So how do I get that? Well, that's just mu2, the permeability in material 2, times the field in material 2. Right, so that is 2, the relative permeability, which is given in the problem, times mu 0, which is 4 pi times 10 to the minus 7, should be a minus there, times h2. So I'll let you, again, punch in those numbers, and what I see on my calculator, up to 3 significant digits, is minus 20.1 ax plus 30.2 ay plus 10.1 az, and that is in micro. Micro is 10 to the minus 6 Webers per square meter. That's what I get, and that is the end there.